All right, today we're going to jump in again and talk about some other options and the options we've been discussing in linear regression. Going to jump in and have some examples of how we use them, how we understand them, how we interpret them, because I think the options are a little bit overwhelming. We've done a lot so far, and there's even more we can do. Then we're going to jump in and have a conversation about how we can make some choices about what to do. So, one of the things I find funny as I teach more and more people about data analytics is that everybody wants to jump into the fanciest of models. And while fancy models have their place, and I've used many of them, and there are many I haven't used, there are many, many choices, and there are reasons for all these fancy models, multiple regression is a sort of a solid workhorse for a reason. And we can do a lot with it, but we need to make some important choices about what we want to do. So why are we using multiple regression? For a couple key reasons. One of them is that, why are we adding complexity to simple relationships? One of the things that we can do here is we can add variables to address omitted variable bias. So instead of having one model of one relationship and one model of another, we take one into account to understand the other, right? So we're balancing against the omitted variable bias and how one thing influences another and how variables play off each other. And this is especially important if we want to make inferences, especially about our x's, right? We looked at that in the sort of cases with re-enlistment bonuses. We've looked at it in the case of congestive heart disease. So all of these, right, these cases of where the omitted variables are really important for what we can understand about the influence of our x on the y. So very important if we want to make any kind of causal statements at all to be thinking about omitted variable bias. When omitted variable bias is present, it makes the marginal effects of the variables we have inaccurate, to put it in sort of technical language, right? We don't really know the influence of x on y if we have omitted variable bias. And including these variables to address omitted variable bias is only really necessary, so to use the control variables, if that omitted variable is related to both the y variable and the x variable. But there's another reason we might want to include additional variables. This is the kind of reasoning that the ISLR book depends on more heavily, and this has to do with that they're important for prediction, that we can explain more of why, right? So these variables need only to be related to y to help out if what we're trying to do is predict better. And we're going to make our choices about what to include based on what helps improve prediction when that's what we're looking for. Here's a fun example. Multiple regression is everywhere. This one's kind of funny, so I thought I'd include it here right? It's just a great name, right? Do you have any idea how to say that title? At any rate, what they were measuring in this paper was sort of subjective measures of beauty and how well teachers' course scores and class ratings were. So, bizarre and interesting, right? Studies of all kinds of things. It's everywhere. And as we've taken on linear regression and now multiple linear regression, we've made our models work hard by adding more variables. And so far, we've added continuous variables, categorical or dummy variables, and some different nonlinear variables that can be used in a linear equation. So essentially, the computer doesn't know they're not linear when we take a logarithmic or quadratic transformation of a variable. So let's take a look at an example just to refresh some of these things that we've done. We're going to take a model that's about predicting housing prices, and it's going to predict it based on crime rates. So this is the median housing price in a neighborhood based on crime rates, the nitric oxide concentration, the average number of rooms in a home, the average distance to 5 employment centers, the access index to the radius of highways, property taxes per $1,000, average student-teacher ratio, low status, right? The percentage of people in a neighborhood with low status, and it also includes some logarithms of that stuff, though we're going to use R to calculate our logarithms. All right. So let's say our dependent variable is price, and we want to see how does price relate to the number of rooms. This is kind of like price per square foot. So it looks like as the number of rooms goes up, certainly so does the price here by $9,119 for the addition of a room. So in our simple linear model with only one variable, rooms matters a lot. Turns out when we add some other variables about the neighborhood, right? So instead of just the average size of the house, as the crime rate goes up, not surprisingly, it brings the prices down. As property taxes go up, those bring your prices down statistically significantly. Distance, it looks like, from the 5 centers in this model doesn't do much, but those 2 variables do. They're all continuous variables. And so we can, and they seem to have an impact on how big of an impact rooms has. So rooms isn't as, right, it's flattening out when you take into account these other things, which means that probably, right, bigger houses are associated with places perhaps with higher property taxes or other things that, or greater distance, and that could be what's accounting for some of that omitted variable bias here. As we've added, right, multiple variables, you might take a look down at your R squared, adjusted R squared. We'll talk about the difference in a little bit, but that the adjusted R squared is getting bigger. We're explaining more of the variation in our model. That's not a bad sign. And our F statistic is getting smaller, which is also not a bad sign. All right. We might also want to take a look at using dummy variables. So I thought what I would do is code something here to create a factor variable for crime level. So instead of having crime level be a continuous variable, which is what I was using, I decided to look at low, medium, and high crime neighborhoods, because sometimes it's nice to just be able to break things into categories and bins. So I went ahead and binned our data. That's my code. And I used that in my regression. And this is what I get for, right, some output. So rooms, still a big, significant, positive impact. But now we have crime level low and crime level medium that also have that impact. These are relative to crime level high. So I let R make the choice of how to do it. And so what this would kind of tell you is that, right, it would allow you to use either of those to make a prediction. So let's say we want to estimate a 6-room or 3-bedroom house in high, medium, and low crime areas, right? So if we had an area where houses were on average about 6 rooms, if it had high crime, that would be, right, about, the house price would be about $18,000. If we had medium crime, it would be about $21,000, and if we had low crime, about $22,000. And there's some code for you to do the predictions in R instead of laying it out. But if you kind of lay it out, right, you get the intercept plus the slope coefficient on rooms times the number of rooms plus the deltas for each of those crime levels. All right. Maybe we want to take a look at this in logs. And logs make everybody crazy, but let's talk about logs for a minute. Right, we talked about that we use logs when numbers are big because we want to bring them kind of back into scope. So if we find some outliers, we might want to think about using logs to tidy up our data and make it make sense. We also might want to use logs because we want to talk about things in percentage terms. And so it allows us to say, right, a change in the number of rooms changes the price by such and such percent. So a 1-room change here leads to a 0.29861 times 100% change, or about a 30% increase in prices per room. So we used here, we have a log level formula on rooms because it doesn't really make sense to talk about percentage change in the number of rooms. So I didn't take the log of rooms. I took the log of price because prices have a lot of variability and it might make sense to kind of tone that down with logs. I took the log of property tax again because of all that variability. And because a percentage change, right, makes sense when we're talking about something like a property tax. But for rooms, what we're talking about here is that a one room change would lead to, and we would go up to our table, look up what a log level model says, and it says 100 times beta 1 change in X. So it gives you the percentage change in Y. Here, we also could have a 1% increase in property tax leads to a 0.4% reduction in price because we have a log-log model there. And so then that's just a straight 1% to another. All right. I find having that table handy, again, whenever I want to do a log model, because it's somewhat confusing to try to figure out exactly how to interpret all of those coefficients. We talked about quadratic models. Here's a quadratic model where we took the distance squared of neighborhoods. So we might think that, right, on some level, an increase in distance might make prices go up to a point and then down after a certain point, or vice versa. And so here it looks like we have that prices are going up to a point, and then there's a turning point at which moving farther away actually starts to make prices go down. So it's an index variable. I'm not sure exactly what it means, but a 1 unit increase in distance would change the price according to this formula. You would take beta 1, 1737-ish, plus 2 times that beta 2, which is negative 128, the coefficient on the distance squared. And we're at distance 4, so we need that x. We know we're at distance 4. That means that a 1 unit change in distance from unit 4 would change your price by $713. We can also calculate the turning point in this model. That falls at 6.8. All right. Now, those are things we've talked about already, and there's even more we can do with our simple multiple linear regression models. Quadratics are not the limit. Those fancy squiggly lines you see, you can use the formula poly to include higher order polynomials in your model. These may not have logical reasons to be included, but may improve fit. So this is something that comes up later. We're going to talk about overfitting later and some of the problems with that. But often when we start to include higher order polynomials, I don't have any logic for how a cubic relationship looks. And if we do this, the model should include the highest useful polynomial and all the other ones under it. So if you use x cubed, you need x cubed, x squared, x included in your model. Probably more useful on a day-to-day level than higher order polynomials is combinations of variables. So in addition to the variables individually, we can multiply them by each other. So we might have some sort of interaction terms. Here an example is that we think that low status and crime together might have a different impact than low status and crime separately. So we estimate essentially, you'll notice that the second model and the third model are the same. I use slightly different code to do it. There's a shortcut. If you multiply low stat times crime, you get low stat crime and low stat times crime. Or you can add the interaction term independently with a colon in R. Anyway, so I ran it both ways for you. And indeed, that interaction term is significant there. And you'll need, again, another formula or to keep things in mind and know where you are in terms of one variable or the other if you want to interpret a change. So we need to interpret at the value. So we need to figure out where we are in terms of crime to understand how low status changes prices. So if we're at crime is equal to 3.6, a percentage point increase in low status would change the price negative $548.74. All right, we can interact dummy variables too. I find this is handy frequently. So often we might want to know, is there a differential impact on something like gender and education? So does going to college have the same impact on income for women as it does for men, might be the question that we have here. Or we might want to ask about race in college. Does going to college for Hispanics have a different impact than, ethnicity, than white and going to college, right? So we might ask those kinds of questions, and interacting those dummy variables helps us do it. Just make sure you go through your list if you're going to go and use that model, and make sure you sort of tag the ones and zeros correctly. So for example, here, if gender was equal to 1 and high school fail was equal to 1, the model would look like you'd want the coefficient for gender plus the coefficient for high school fail plus gender times high school fail, right? Plus that one. So you would have a 1 there, a 1 there, a 1 there, and then the rest of the model to estimate in that specific case. Finally, you can go ahead and interact sloped or continuous variables with your dummy variables and get these and therefore have specific slopes based on different characteristics. This can be really handy because maybe constraining your model to be 2 parallel lines is not realistic. So for example, in this case, we have students and non-students and how income affects their credit balances. This comes from the book, from the textbook. And it says that basically students and non-students, as they have more income, it has a different impact on their credit balance, right? So students have credit balances that go up more slowly than non-students as they have more income. We can do that here in our in the model that we created before, using crime levels and low status, and an interaction term for crime level and low status. So that would say an increase of 1 percentage point in low status in a low crime, medium crime, or high crime neighborhood would have different slopes. So the slope in a low crime neighborhood would be negative 580, right, for every increase in status in low status people in that neighborhood. A 1 percentage point change in low status in a medium crime neighborhood would reduce housing price $417. And in a high crime neighborhood, more low status people would decrease prices by $698 for every increase in low status people. So kind of weird nonlinearity there too. That's kind of interesting that it comes out when you use the dummy variables and the different slopes and categorize things instead of keeping a variable continuous, that the bins have different impacts. Kind of interesting, but that's neither here nor there. Not the point that we discovered some wacky, cool nonlinearity. You're so excited. I'm so excited. But that it's a way to kind of, sometimes binning helps us see the data differently. And so in this case, it allows us to see these 3 different slopes and what they mean. And we need to know where we are in terms of low status and rooms and what kind of crime neighborhood we have in order to make our prediction. And this is what that prediction would look like. So, are you convinced that it's worthwhile to spend a little bit of time on linear models? I always disappoint students by telling them they have to do linear models. Everybody thought we were going to jump ahead to non-linear, non-parametric, unsupervised learning models, but these linear models can do a lot. They can even do more. And we're going to talk about that moving into next quarter. We're going to do more with linear models. But given all of the things you can do with linear models, the most pressing question I think we need to get to today is, how do we make choices about the right linear model for the right circumstances?